Oh, hi everybody. This is what we call in science an orange. And what gives an orange, or at least what helps give an orange its unique odor and taste, is an ester called octyl acetate. An ester is a compound that results when you react a carboxylic acid with an alcohol. Here's a banana. And what gives a banana its unique odor and taste is an ester called isoamyl acetate. And so if you synthesize this in a lab and you put it in candy, it'll taste like a banana, even though that didn't come from anything but a test tube. And this is a bottle of rum, or at least it used to be. I kind of drank most of it. And what gives rum its unique kind of odor and taste is another ester. And how about these things? Coconut oil and olive oil are what we call triesters of glycerol. And this is how you store energy in the form of your fat. Those are esters where the alcohol that's the backbone is glycerol. And then carboxylic acids are the fatty acids. And they're big old molecules that you use for storage. And then, of course, whether it's solid or liquid depends on how saturated they are. So let's talk about esters, and then we'll also talk today about amines. And in the meantime, I'm going to make the weirdest smoothie ever. Hi everybody, hi, Mike here, and we're going to continue and put a nice bow on organic chemistry. Last video we invited oxygen to the party. Today we're going to talk about more compounds that have oxygen, and we'll also invite nitrogen to play. So today we're going to talk about esters. These really touch your life, as you saw, so we're going to do a deep dive into esters. And you know, you should always do a deep dive. Like, don't do a shallow dive. I did that when I was a kid and I got a bump on my head. Okay, so then what we're going to do is we're going to talk about what an ester is. An ester is a carbon chain connected to a carbonyl group, C double bond O, connected to an O. Now up to this point it looks like a carboxylic acid. You put a hydrogen there, that's a carboxylic acid, and actually that's how you can make esters is from carboxylic acids. But if we add another carbon chain, the reason we say, of course, R prime is it could be the same length or different length or branched. And that's now an ester. The way you synthesize esters is you take an alcohol and react it with a carboxylic acid. Now, in order to make this a little bit more explicit, I'm showing you the carboxylic acid turned around. It doesn't change the fact that it's a carboxylic acid in the alcohol. And then what happens is it's a very complex mechanism, and you know about mechanisms, but when you take organic chemistry, and some of you are destined for organic chemistry in the next course, you always talk about mechanisms, but I can just tell you one thing. Go pick up your biology book, or just think about combustion. Whenever you have water formed, that's usually a product favored situation. Now, don't think about it too hard. You're like, you mean the acid gave off an OH? And remember, it's a complex mechanism. What happens is when you take acid and you apply it to something with an OH, it is very, very helpful in converting an OH group to water. It's called what we call a good leaving group. All right? Let's hold off on that until you take organic chemistry, but just basically the two chains come together and you make water. So, you know, dehydration, synthesis, combustion, making a protein out of amino acids, all those things produce water and usually are very favorable by nature. So now let's talk about how we got the name. You take the part of the name that came from the alcohol, and now you got to use the old school style of naming things. So instead of calling this 1-propanol, we just kind of call it propyl alcohol. And instead of calling this ethanoic acid, we're going to use the old school names and call it acetic acid. And now you get propyl acetate. So it's really simple. You just smash the names together. You lose the term alcohol, and then you also lose the term acid. So let's do an example here of a synthesis of an ester, and we'll just kind of pick at random something else. Well, it ain't random. I figured it. I already thought about this. So we've got this particular alcohol. This will be butanol, but actually we're going to call it butyl alcohol. We're going to use the old school naming scheme. And then we've got formic, not methanoic, but the old school name, formic acid. And then we will combine the name, the part of the name from the alcohol. And when, I didn't mention this in the last example, when you take, well you know this, when you take an H plus off of an acid, we use the suffix ate. So for example, nitric acid, its conjugate base is nitrate, and so that's where the rest of the name comes from. But first, let me go and put these two things together, right? So you can have a 4-carbon chain, and that part came from the alcohol, and then you got the C double bond O, and then the part that came from the acid. And so the name of it would then be butyl formate. Whoops! Guess what I forgot? One of the most important things in the universe, plus water. So that's generally you just smashing the two chains together, taking the two names and also smashing them together. Now I'm going to try to make this interesting for you because I want to talk, as I showed you, I had coconut oil in the intro, and here's what happens inside of you. We have glycerol. Now if you look at that, that's very water soluble, and then so are carboxylic acids. And what happens is when we have very, very long carboxylic acids, they're usually even numbers because when we use them for energy, we bust them off by twos. That's called beta oxidation. For you biochemistry majors, you'll have fun with that. But you see, I made 3 different R groups, and what happens is, well, whatever's available in the organism that's going to store this, it stores it as triglyceride, which we know, that's in your diet, right? If you have coconut oil, that's actually a triglyceride. The oils that are in, and it's funny because coconut oil is actually solid. So we use the term fat for things that are solid, and we use the term oil for things that are liquid. But coconut oil gets a bye somehow because it's from plant sources. Most plant sources are fats and not oils. And why are they solid or liquid? Well, it depends on how these things stack together. So keep in mind, this is triglyceride. Now, look, ester, right? You know, carbon chain, C double bond O, carbon chain, and you know, this would be the backbone of it. Now, what's in those R groups depends on if it's solid or not. So if it's saturated, what happens, gang, is these things, you know all about intermolecular forces. Saturated hydrocarbon chain, remember, these are 12 to 24 carbons long. You're going to find that they're straighter. You know, let's take a look at it. It's saturated. What would that look like? It'd be like, you know, a bunch of this stuff. You know, the R part. But if you throw a double bond in there, depending on how it's oriented, especially if it's a cis, you know, you will throw a kink in there. You know, that would be bent at 120 degrees, you know, so I should have made that going down into the paper. Let me do that again. So, you know, it'd be trigonal planar. Now, think about this. You're going to throw a bunch of paper clips in a pile, and all the paper clips, none of them been bent. It's going to be like packing saturated triglycerides together. But if you take them apart and you bend them and you put a big kink in them, they're not going to pack as closely, and their London forces can't act as effectively. And so that's why they don't pack as close, and they're less dense, which makes them a liquid. So you can make the, you know, broad brush example to say that the more double bonds you put into triglyceride, the more likely it's going to be liquid. For example, they even use terms, right? Omega-3, that's the position of the double bond. They're talking about double bonds there. But if you had something like beef tallow, that would be a lot of saturated, or coconut oil, and they pack together, and so it's kind of disgusting. But if you go and you go out to eat, and you get a steak, right? And then you throw it in the leftovers. And who has leftovers when you eat steak? Not me. But you know, if you did, you come back the next day, it's all congealed and stuff. And I know that was kind of gross, but it's really chemistry going on that makes it do that. It's packing of molecules. So let's switch gears a little bit. We're going to invite nitrogen to the party next. Let's have some music or something. All right, guess what's next? We're going to talk about amines, if you want to sound fancy. Sometimes they call them amines. I don't know. It makes me feel weird. I've always called them amines. Hey, look at the beginning. Ammonia, amines, AM. And so you find out that a lot of the nitrogen-containing compounds start with AM. And so this is ammonia. And what if we throw some carbon chains on it, like just a methyl? Let's do a methylamine. That would now be an amine. So, you know, an amine has to have carbon chain in it. So ammonia is an amine, but it's a derivative. An amine is a sort of derivative of that. And it's real simple. We would call that methylamine. And by the way, some of these things aren't that great for you. And I think if you watch Breaking Bad, which I haven't, by the way, I've just watched season 1, but they hauled a huge, they stole a huge train car full of methylamine. And it's super toxic, but they use it in bad things, as you saw. And I got to watch the rest of Breaking Bad. I'm a chemistry teacher who has had cancer, and I haven't watched that. I'll get on it when I retire someday. So this would be methylamine. Now what we do is we say however many sites of the 3 of nitrogen are occupied, we give them sort of classification. So we would call that primary amine. And you know, you'll see why we care. It has to do with the mechanisms of reactions later on. Here we're going to put 2 carbon chains on. That's a dimethylamine. You could see dimethyl, and that would be a secondary amine. And then finally, if I go put 3 chains on there, and it doesn't have to be methyls. I could have used, you know, methylethylamine or something like that, or triethylamine. I'm just trying to make this simple. That's a tertiary amine. And this has to do with how well they are stable in making a charge, which actually this will probably look very familiar to you. Go look at your KB chart in your book, whether it be the OpenStax book or whatever. The reason nitrogen-containing compounds are bases, they're weak bases, they're in biological organisms. Heck, in biology we call them nitrogenous bases, and that's because they're Lewis bases. So you know what happens is they've all got nitrogen, and nitrogen always has that trigonal pyramidal, remember Gen Chem 1 shape with an extra pair of electrons, and if you go throw an H plus at it, it'll take it. It's an electron, it's a hydrogen acceptor, which makes it the opposite of an acid, and that's how something like ammonia or amines can then neutralize or you know, be a H plus taker, which is the opposite of an H plus donor, so that's why it's a base. And of course, back to formal charges, when you do put 4 bonds on a carbon, you got a formal charge of 1. And so what you've done is you've got, you know, acid, base, and then, you know, conjugate. I should have done this, gang. Look at me, screwing up, not putting a double arrow in there because most of them are weak. Conjugate, acid, conjugate. I know you're sick of all the acid and base stuff, but that's the reason. It's the electron pair that makes these things what populate the majority of your KB chart. All right? And they're all weak. Hey, what is this? What's that thing? Hey, it's a carboxylic acid and an amine. And that is an amino acid. Sound familiar? You folks who take protein powder know what those things are. And you got 20 of them. And what makes them unique is this chain. All of them have this, you know, acid, amine, hydrogen, the side chain. That's called a side chain. And you know what will happen? If you take another amino acid and put it by this amino acid, they will form water, and that would then be a dipeptide. So they'll react with each other. What will happen is this, let me try to draw another one real quick, and then I'll let you go. All right? It's been a long semester, and I know. But this is really good that you're getting this exposure here. And anytime you got a nitrogen, you got the ability for something like this to take, oops, it's the nitrogen doing the heavy lifting, take that, and then what happens is, you get rid of a water here, and they join together, and that would be called a dipeptide. What happens when you have 50 or more amino acids? Now it's not a peptide, it's a protein, right? Insulin, for example, has like 51 amino acids. Now it's just barely big enough to be called a protein, and they have it was supposed to be HOH, water. They have different characteristics because there's different classifications. Some of these R groups are hydrophobic, and then that would be a protein. If you had enough of those kinds of amino acids, it wouldn't dissolve in water very good. So you'd say, hey, well, when I take a shower, I don't dissolve, right? But if you had something that was soluble in water, you'd have a lot of these R groups that would be polar. And they'd be kind of like a big globule, where all the polar ones are on the outside and all the non-polar ones on the inside. If this stuff turns you on, you might want to continue going on past organic chemistry into biochemistry, because that's a lot of stuff in the future that's biochemistry. Heck, folks, a lot of you are probably biology majors, and I appreciate biology majors because I had my COVID shot yesterday, and yes, I feel like got hit by a train because it was my second one, but I'll push through it. Okay, so thanks for watching. This is the end of chapter 20, really. And so if you're headed for your final exam, good luck, and good luck with everything, because this is usually the end of Gen Chem 2, is this particular chapter. So, and good luck if you're moving on to organic chemistry. Keep your notes, because you will need them. See you later, folks. Bye.